So this is a video about another kind of cell. It's an electrochemical cell, but this one is different from the one we previously discussed. Here's the one we previously discussed. So look at that. Look at this. What's the big difference? Well, one of them's got color, but that's not the difference that I was looking for. So the difference is this one that we talked about earlier, where you're actually creating a flow of current by making a chemical reaction occur in such a way that the electrons have to go through a wire. In this one, we're actually putting energy in. So in this one, we're creating the ability to do work. And in this one, we're doing work on the system instead of work being done by the system on the exterior. So this one requires energy going in. So this is the symbol of a battery right here. Electrons flow out the negative terminal over here, and they come in through the positive terminal. So if you take a battery, if you take a 9-volt battery and touch it to your tongue, you'll feel this happen. If you have, but don't do that because it burns. If you put the two pieces of metal into a solution and connect them to a battery like this, Me here stands for metal. And this is a piece of copper here, which is going to resupply copper ions. And you start pumping electrons into this piece of metal, which is sitting in this case, a copper sulfate solution. What will happen is the copper ions, the Cu with a +2 charge, will move over to this electrode and pick up electrons and turn into copper metal. Now this was not copper, this piece of metal, so this could have been anything, could have been a quarter, could have been a dime, but it'll become plated with copper metal with 0 charge. That's a 0. So this is the idea of electroplating. At this anode, electrons are going to be leaving, so you'll have the copper ions losing electrons, so they'll be doing this. And so you get more and more copper ions, and it just keeps cycling through. Copper comes off of here, plates over here, as long as you're pumping energy into the process. Now it doesn't have to be copper, it could be silver ions. So if you had silver ions and you pump electricity into the system, you're going to get silver metal. And that's how you make silver-plated silverware, silver-plated jewelry. Could be gold, gold plating. So this is the idea of electroplating. Now, of course, you can quantify this, and that's what Chapter 26, Section 3 is about. So let's take a look at Chapter 26, Section 3. These are Faraday's laws. Faraday was a famous electrochemist. So a couple of basics. There's a unit of electric charge called a coulomb. And a coulomb, the amount of electric charge that it takes to deposit a mole of electrons is 96,500 coulombs. So 96,500 coulombs is the amount of charge that it takes for 1 mole of electrons. And that is known as Faraday's constant. On the AP test, they'll give you this constant. They might not round it off quite this much, but that will be given to you. All right, so Faraday's constant, the amount of energy that it takes, or amount of charge it takes to equal 1 mole of electrons. Now a coulomb equals an amp second. Amps times seconds. So a coulomb, by definition, is an amp second. So let's take a look at an example problem, like example 3 here. How many grams of aluminum will be deposited if 31,500 coulombs of electricity pass through an aluminum nitrate solution? Now you know that aluminum nitrate, when you put it in water, dissociates like all soluble ionic compounds. Like that. No equilibrium because it's a soluble salt. And so we have these aluminum ions floating around in solution. So if we have 31,500 coulombs that we're of charge we're putting into it, and we know that 96,500 coulombs would deposit 1 mole of electrons. And we also know that for every 1 mole of aluminum ions, there would be 3 moles of electrons. Now, in other words, if we're going to make the aluminum become aluminum metal, like over here, remember we had the copper required 2 moles of electrons to make it become copper metal. The silver requires only 1 mole of electrons because it only had a +1 charge. Aluminum is going to require 3 moles of electrons because aluminum has a +3 charge. So that's where I get the 3 moles of electrons. And then if we wanted to find out what mass that would be, we just change moles to grams. So we know that there are 27 grams of aluminum in 1 mole. And that's true whether we're talking about aluminum ions or aluminum metal, because the subatomic particle that you lose when you become an ion is electrons, and their mass is so negligible that we ignore them when we do the formula mass. So 31,500 times 27 divided by 96,500 divided by 3, you would get 2.94 grams. So that's one type of Faraday's law problem that you might run into. All right, another one, example number 4, just work through their examples. They have 10 amps of current, so 10 amps, and it's flowing for 20 minutes. Now, didn't we say a minute ago that a coulomb is an amp second? So really, we can multiply these together and find out how many coulombs we have. The only catch is that we need to change seconds to minutes. So minutes to seconds. So we'd have 20 times 60. So we really have 1,200 seconds times 10. So it'd be 12,000 coulombs. Okay, so 12,000 coulombs. All right, we know that it takes a mole of electrons for 96,500 coulombs. Right, so we put coulombs on the bottom, we put moles of electrons on top. 1 mole of electron, 96,500 coulombs. So that would tell us how many moles of electrons we could deposit. And we want to know, we're taking this through copper 2 nitrate. So I didn't mention this, but copper 2 nitrate, of course, when you put it in solution, it's going to turn into copper ions and nitrate ions. So how many moles of electrons does it take per mole of copper? So you'd have 1 mole of copper. How many did you think it was? It's +2 charge, so if I make it go to copper metal, it's going to take 2 moles of electrons. Right? And the question only asks us how many moles of copper will be deposited. So we're finished at that point. And the answer would be 0.0622, just off the top of my head. And also looking at the book. So that's moles of copper. All right, so that's how you handle a Coulomb's law kind of problem. We'll do example 5. Might as well do that one too. So we're going to find the mass of silver metal that can be deposited. 5.12 amps goes through for 2 hours. So you have 5.12 amps, 2 hours. You really need to know how many coulombs you have, right? So 2 hours. But hours are not seconds, so we have to change to seconds. So let's do that real quick. And we have 5.12, well, I'll do the second part first. So you got 2 hours. There's 60 minutes in an hour, and there's 60 seconds in a minute. So we're really looking at 7,200 seconds. We're going to multiply that by 5.12 amps, and we get 36,864 coulombs. All right, and we want to know the mass of silver metal. And we have silver nitrate. So silver nitrate is AgNO3, and Ag is +1, so silver plus and nitrate minus. And so each mole of silver will require 1 mole of electrons. So we would have coulombs on the bottom, we'd have moles of electrons on the top, and we know that 1 mole is 96,500 coulombs. That's Faraday's constant. Then we would put the mole of electrons on the bottom and moles of silver on the top. So 1 mole of silver is 1 mole of electrons. Oops, got moles. And the formula mass of silver, if I remember right, is 108. But I'll double check that real quick over here on the side. Yeah, 107.9, so we just call it 108. So we put grams on top, we put moles on the bottom, and 108 over 1. I guess I could turn the page. That would give me another place to look up the mass. So you end up with 41.3 grams, what you should get. Okay, so those are the basic kinds of problems that you will end up with on using Faraday's laws. And so back to the beginning, a coulomb. Get this out of the way here. So 96,500 coulombs is equal to a mole of electrons. That's called Faraday's constant. And a coulomb is equal to an amp second. You need to know that definition. All right, I'll stop that one. So you should be sure you can handle all of chapter 26.